This is the beginning of section 12.2. It's about measures of central tendency, and what that's really all about is that when you have a data set, you like to know what number would be best representative of that data set. And it happens in life all the time that people ask, what is the average income? What is the average size of a house in 2000? And what's the average size of a house in the year 2018? And so a lot of averages that people want to know. What is the average income for someone with a bachelor's degree in history or in engineering? And so people want to know what would be a representative number. Turns out there are different ways to measure these central tendencies. And so the objectives in this section are about finding and interpreting the mean of a data set, then finding and interpreting medians, and finding and interpreting modes, and then applying this infer central tendency measures from stem and leaf displays. We've done this in the previous section. And then discern symmetry in data sets. And last but not least, compare measures of central tendency. Well, I put that last part in the beginning because it gives you a good overview of the things that we'll be discussing here. And of course, we go into more detail as we progress in the section. But we begin with a mean, and the mean is of a set of numbers is found by adding all the values in the data set and then dividing it by the number of values. And most of you have done that, and so that's a concept that most people are familiar with. The median, excuse me, the median is a middle number. So to find the median, we first rank the values, and then for an odd number of values, the median is the middle value in the list. And for an even number of values, the median is the mean of the two middle values. So it may sound a bit mysterious, but we'll get to that. And then a mode is a value that occurs with the greatest frequency. Some sets of numbers have two most frequently occurring values, and they're called bimodal. Other sets have no mode at all. If no value occurs more than once, then the others, or it must be more than two values occur most often. So the mode is really pretty easy to find. So a single number that is in some sense representative of a whole data set of numbers is a kind of middle value that would be a measure of central tendency. So we begin with a mean, and it's the most common measure of central tendency, or it's also called the arithmetic mean. And the mean of a sample is denoted x bar, while the mean of a complete population is denoted with a mu, the Greek lowercase letter, the Greek letter mu. And for our purposes here, data sets are considered to be samples, so we use x bar for the mean. And so it's also in everyday language called average. So the mean of a set of data items is found by adding up all the values, all the terms, and then dividing the sum by the number of items. Again, that's what most people associate with the word average. Because adding up or summing a list of items is a common procedure in statistics, we use a symbol for summation that looks like this. There's a capital Greek letter sigma. It's a capital S, so to speak, for sigma. And so therefore the sum of n items, say x sub 1, x sub 2, x sub n, can be denoted by this symbol here. The sum of all x. And therefore, the mean of n data items is calculated as follows. X bar is the sum of all the data items, x sub 1, x sub 2. And again, that's all contained in a symbol summation of all values of x divided by n, and that is how many data items we have. So, as a very simple example, let's compute the mean of the following data set. The numbers are 305, 285, 240, 376, 198, and 264. So we compute x bar in the following way. So here we have all the data items, 305 plus 285, etc., all the way up to 264. And then there are 1, 2, 3, 4, 5, 6 data items, so n equals 6. And when we add this all up, that's 1 equals 1,668 divided by 6. And that's equal to 278. So we say x bar is equal to 278. So you can see that it's very, very simple. Now sometimes there are some things called weighted averages, and grade point averages are an example of that. And of course that's something that most of you are concerned about, your grade point average. And so here's an example how we do that. So let's say someone takes some classes, a mathematics class, and a history, and a physics, and an art class, and a PE class. And here are the grades that the student earned. Like an A in mathematics, a C in history, a B in physics, a B in art, and an A in PE. And then here's the grade points. And so we know that an A counts for 4 grade points. We know a C counts for 2, a B counts for 3, again 3, and an A counts for 4 grade points. And then there's a matter of the units. And so math is a 3-unit class in this case. History is a 3-unit class. Physics is a 5-unit class. That seems like it's a lot harder, and it usually is. And then art is a 2-unit class, and then PE is a 1-unit class. Okay? So here's how we do the grade point average. So the first thing we do is we multiply the grade points times the number of units. So 4 times 3 equals 12. And 2 times 3 is 6. And 3 times 5 is 15. And 3 times 2 is 6. And 4 times 1 is 4. Then we add up all the grade points times the unit. So here the total is equal to 43. We add up these numbers, it's equal to 43. And when we add up the units, the student carried 14 units. So then the grade, here are the totals. So then the grade point average is simply 43 divided by 14. 43 by 14. And that's equal to about 3.07. So that would be the GPA for this student. So in case you ever wondered how the grade point average is computed, here you have the details on that. And this might also help you keep track of your own grade point average before it's published by the college. Next, we'll be talking about the weighted mean of a frequency distribution. So the weighted mean of n numbers, x sub 1, x sub 2 to x sub n, that are weighted by the respective factors f sub 1, f sub 2 to f sub n, is calculated as follows. W bar, in other words, the weighted mean, is equal to the sum of all the factors of x times their frequencies divided by the sum of the frequencies. In other words, the weighted mean of a group of weighted items is the sum of all products of items times weighting factor, divided by the sum of all the weighting factors. To explain this a little bit, we will look at an example. Here's the example. Finding the mean of frequency distribution of salaries. Okay, so here we are asked to find the mean salary for a small company that pays annual salaries to its employees, shown here in the frequency distribution in the mark, here on the left. Okay, so what we have here is the salaries, X, the amounts that people are getting paid, and the frequency would be the number of employees who are receiving that kind of salary. In other words, 8 people who make $12,000 a year, the 11 people making $16,000 a year, etc., and 1 person making $50,000 a year. So here we need the third column. That's X times F. So X times the number of times the frequency. So we multiply 12,000 times 8, we get $96,000. 96,000. And 11 times 16,000 is $176,000. And 14 times 18,500 is $259,000. And 9 times 21,000 is $189,000. And 2 times 34,000 is 68,000. And 1 times 50,000 is 50,000. So next we need to add up all the frequencies. 8 plus 11 plus 14 plus 9 plus 2 plus 1 is equal to 45. And I pre-added these numbers for you here, and that is $838,000. Adding up all the product of the value of X times its corresponding frequency. So that would be 838,000. And then for the mean salary then, we divide 838,000 by 45, and that is equal to about 18,622. So that is the mean salary, calculating it this way. Now note the difference. If we had not taken into account the weighting factor, in other words, how many people actually earn the salary, if we'd simply added up all the salaries, that would have been equal to 151,500 divided by 6. And so that would have been $25,250 average salary if you simply added up the salaries. Why would that be not correct? Well, first of all, this is a more realistic average, the mean salary, because here we give as much weight to 50,000 as we would do to 12,000 if we simply added up the salaries. So this kind of calculation is really, really important here as an exercise, but also in the real world. Next, we're going to talk about the median the middle number, so to speak. So another measure of central tendency that's not sensitive to extreme values, high or low, is the median. So this measure divides a group of numbers into two parts, with half the numbers below the median and half above it. It's a very simple concept. Now to find the median, we have to do something, and typically we need to group the items. Number one, we need to rank them. Rank the item sets. We arrange them in numerical order, from least to greatest. Then, if the number of items is odd, the median is the middle item in the list. And if the number of items is even, then the median is the mean of the two middle values. So let's look at this here right away. And so in the first example, A, we notice that the numbers have already been ranked. So there are 1, 2, 3, 4, 5, 6, 7. So it's an odd number of items. So that means the one in the middle would be 13, because 3 to the left and 3 to the right. So the median would be 13. So that is the median. In example B, the items are not, no, they are actually also in increasing order. Yeah, it's also ranked. Oh, great. So how many are there? 1, 2, 3, 4, 5, 6, 7, 8. So the two middle values are 13 and 18. So we need to take the median, need to take the mean rather of 13 and 18. So that's 13 plus 18 divided by 2. So there would be 31, and 31 divided by 2 is 15.5. So there would be the median. And in the last part, part C, we notice the numbers are not ranked yet. So that's the first step we need to take here. So now we've ranked the items, and we notice there are 1, 2, 3, 4, 5, 6, 7, 8, 9 items. So it's an odd number. So there are 4 to the left and 4 to the right. And so 15 would be the median in this case. So the median is a pretty easy number to find. Now, if you're somewhat familiar with Excel, you can do all of these things in Excel. You input the numbers in Excel and use the command median to compute the median of a data set. And when you only have a few numbers, it's pretty easy to do it like the way we did it now. But if you have a large number of items, like 50 or 100 or so, then the manual method is really cumbersome. And so you may want to try that out in Excel. And so what you can do is you can go to youtube.com and then search for computing mean and median and mode in Excel. And then you'll find some YouTube videos that explain it very, very well. And it's easy to do. You can learn that in less than 10 minutes. Next, we'll be exploring the position of the median in a frequency distribution. So the position of a median would be n plus 1 divided by 2, which means we add up all the frequencies, we add 1 to it, and divide it by 2. Very simple thing, but notice this. This formula gives only the position and not the actual value of the median. So in the following example, we're going to investigate this. To find the median for the following distribution. So here are the values for x, and here are the frequencies. So again, here are the values, and here are the corresponding frequencies. And what we're going to do is we arrange the work as in vertical columns. And what the values are listed here, 1, 2, 3, 4, 5, 6. And the corresponding frequency is arranged this way here. And then the third column would be the cumulative frequency. Now you've seen this before, the cumulative frequency, when we talked about frequency distributions, but we never really explained why we need that. And so now here you see why this is important to know. So the first value would be 1. And then to the 1, we add the next frequency would be 3. So 1 plus 3 is 4. Then we add the 2 to the 4 to give us a 6. And then we add the 4 to the 6 to get a 10. And we add the 8 to the 10 to get an 18. And then the 2 to the 18 to get a 20. So in other words, this tells us for each value how many items have that value or a lesser value. So the sum of the frequencies equals 20. And then from the formula we looked at a moment ago, the position of the median is the sum of the frequencies plus 1 divided by 2. So in other words, there would be 20 plus 1 divided by 2, which would be 21 divided by 2, or 10.5. So that's the position of the median, 10.5. In other words, it's between the 10th and the 11th item in the list. Now to find this item, or these two items, we make use of the cumulative frequencies. Now the cumulative frequency tells us that 4 has a position of 10, so that means 5 would be the 11th one. So it would be 4 plus 5 divided by 2. It would be 9 divided by 2, or 4.5 is the median. So that's our median for this distribution. Again, from 10.5, we find that number 4, or the frequency of 4, has a 10th position, and then 5 would be the next one. So 4 plus 5 divided by 2 would be 4.5, the median for this frequency distribution. Next, let's talk about the mode. It's a very simple concept, because the mode of a data set is the value that occurs most often. So here's a data set, 51, 32, 49, 49, 30, 74, 81, and 92. And notice they don't have to be in ranking or anything like that. So we notice that 49 occurs more often than any other number. So 49 is the mode of this data set. Then we look at the next data set, and so 482, 485, 485. So 485 occurs twice, and then we have 487, 487. So in other words, this is a bimodal set. So there are two modes, 485 and 487. 485 and 487. So a data set can have more than one mode. And when you look at the data set C, you look at all the numbers, and you see that no number occurs more than once. So this one does not have a mode. So no mode. And when you look at the frequency distribution, it's really quite simple, because the frequency tells you how many times a number occurs in a data set. So the number 19 occurs once, and the number 23 times, and number 22 8 times, and so on. So you look for the highest number, which is 8. So then the mode of the data set is 22. So modes are relatively easy to determine. And again, that's also available in Excel. The mode command, you can find what the mode of a data set is, in case it's a huge data set. And again, it may be more than one mode. So I highlighted the bimodal data set to make sure everybody gets that and understands what it looks like. As we had seen before, data is sometimes presented in a stem and leaf display in order to give a visual impression of the distribution. In other words, it's like a histogram just turned on its side. We can also calculate measures of central tendency from a stem and leaf display. The median and mode are easily identified when the leaves are ranked on their stems. And so when we look at this example, scores on a biology exam, so here we are told the display here represents scores achieved on a 100-point biology exam by the 34 members of a class. And remember what that means. So one score was 47, then 51, 53, 56, 62, etc., all the way up to 90, 90, 90, 91, and 96. So what do we do? Well, for the mean, we have to add up all the numbers. So for the mean, we add up the numbers. So in other words, we add 47 plus 51 plus 53 plus 56 and all the other numbers in between, and then towards the end we have 90 and 91 and 96, and we divided by n, the total number, and there was 34. There was 34 in the data set divided by 34, so that is equal to 2,543 divided by 34, which means the mean is equal to 74.8. 74.8 is the mean for the stem and leaf display. So that took a little bit of work. Now the good news is that the median is a little bit easier. First of all, we have the leaves already arranged in proper order, increasing order to the right. So now we just need to count, well, the 34 is an even number, so we count 16 from the beginning. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So we end up here, and then there are 16 on the other side also. So the median is between 77 and 78. So the median is equal, between these two numbers. Remember, that means 77 plus 78 divided by 2. It's an even number, so You have to find the mean of the two middle values. So, and that's equal to 77.5. So that's our median for this data set. Stem and leaf data set. And now for the mode, well, that's really easy to do, because we just look at the number that repeats itself the most, and simply by inspection, you can tell that the 88888 here, 78, 78, 78, 78, 78, is the number that repeats the most, so the mode is equal to 78. Again, that works especially well when the leaves have been arranged in the proper order, and they were in this case. A very useful way of analyzing data sets is depends on, when we look at the distribution, whether it's symmetric or asymmetric. If it's a symmetric distribution, as you can see here, you can move from a central point to the left and to the right, and each one has about half. So we have maybe a uniform distribution in this example A, and here we have one that is not uniform, obviously, but it's still pretty symmetric about its center. And so it's a unimodal distribution, it's only one mode. Here is a bimodal distribution, and that's also symmetric with respect to its center, because the center is here. So it's a pretty easy thing to see whether a distribution is symmetric or not. And again, they're not exactly symmetric in most cases, but they're approximately symmetric. Then you have distributions that are skewed to the left or skewed to the right. And so here we have a left skewed distribution, and here's a right skewed distribution. And one way to remember this, if you ever forget which one is which, look at your feet. Like this would be a left foot, because your big toe is probably bigger than all the other toes. And here there would be a right foot with a big toe here, and the toes getting smaller to the right. Anyway, just a little way to remember that. And so if you have any doubts and need to remember how did it go, that's how it goes. And then here is an example of a bimodal distribution, which also can be skewed, in this case skewed to the left. So that's really just to recognize and understand what is meant by skewed distribution and symmetric distributions. There's obviously a lot more to it, but this is just an introduction. This is a conclusion of section 12.2.